One of the things I tell my students is you have to adjust the talk based not just on the audience, but on the time of day. And so if you really want to, I can give you a hyper-technical talk, or you can wait for some of my students who will give you a hyper-technical talk. What I want to do is, this is right after lunch, I want to try to do something interactive. So out of curiosity, how many of you have seen Sperner's lemma? It'd be really bad if the speaker's hand was not up. Although I never did take abstract algebra while here. So one of the big questions that you have to grapple with is, how do you prove something exists? So what kind of strategies can you come up with to show that something exists? And so I know we have a couple of cubers in the audience. Somebody I think has a slightly better colored cube than this one. I've got pictures of them here. This is the standard cube, 6 sides, 3 by 3 on each side. This one looks a little bit different. It's got 9 on 2 of the faces, but they're in a strange pattern. And the other one's 2 by 3. And so they look extremely different at first. But if you look at them the right way, they turn out to be almost identical. There's no red side, but if I twist it like this, if I hold it at 30 degrees or 60 degrees, if you prefer, you can now see it's 3 by 3. So once you see the right way to look at something, it becomes trivial. So what I want to do today is talk to you about different ways to look at things to try to show that something exists. And so some of this is being done right now with some students I'm working with in the Polymath Junior program. For those of you who are here, you're obviously doing an in-person REU right now, since this is a conference for people doing in-person REUs at Yale and Williams. But if you are interested in mentoring students in future years, especially as you start graduate school, please let me know. We're always looking for people to be involved to try to provide as many opportunities as possible to students. And so some of them are working on problems related to the main topic of today. So one way to prove that something exists is to construct it. Really hard to argue if I can explicitly give you an. So I'm going to assume I don't have to show the details for the first two, solving ax plus b with clearly, we will assume a is not 0, ax squared plus bx plus c equals 0. How did I get that? How did I get the roots for the second one? Yes. So, no, I actually got it by divine inspiration. I just wrote it down. Who believes divine inspiration versus complete the square? Well, here are the 3 roots for the cubic, right? I could claim I got them by divine inspiration. You would be right to be skeptical, right? The solution exists, and there's beautiful ways to find it. You could actually make it a lot simpler by doing what's called without loss of generality. So without loss of generality, what can we assume about the cubic? I'm sorry? You can assume b equals 0. You can translate like that. And there's also something else you can do. Good, but more than a is not 0. What is a? A is 1. So you can always divide by a to make a 1, and then you can adjust and translate to make b equals 0. And that would simplify this a little bit, but it wouldn't be as impressive of a slide. I don't have space at a reasonable font size to show you all the roots for a quartic. I'll just show you one of them. This is why I was so concerned at the beginning, can you read the slides? If you somehow doubt that this is a root of the quartic, that maybe I switched the 27 to 9, what could you do? I'm sorry? Yeah, you can plug it in. So it's not that hard for me to show you that this works. The algebra might not be fun, but I can slough through it. So this is one way to prove something exists. So as an exercise, please write down the roots of the quintic, sextant, and higher. Actually, it was, I think, upstairs and one over when I had Galois theory. All right, so at some point, you can't always write things down. So you have to go for other methods of proving. So, you would have the fundamental theorem of algebra that says a polynomial of degree n has n roots. We're no longer explicitly constructing them, but we're showing that they exist. There was some talk over lunch about Zeckendorf. I'm not going to really talk about these slides. I'm just putting them up here to say there are certain things, certain games where we can show something exists without knowing how to find it. Okay. How many of you have seen Dirichlet's theorem for primes in arithmetic progression? Okay, beautiful, beautiful theorem. So take 2 integers a and b have to be relatively prime. And as long as they're relatively prime, there will be infinitely many primes congruent to a mod b. And the method of proof is beautiful, because it actually answers not just that question, but a simpler question, which turns out to be very hard rather than proving that there are infinitely many primes congruent to A mod B, can you prove that there's one prime? And sadly, the easiest way we know to prove in general that there is one prime congruent to A mod B is not only to show that there are infinitely many primes, but to first order all the A relatively prime to B have the same percent of primes. Therefore, there must be at least one congruent to your A mod B. This is tremendous overkill. But this is one way to show something exists. Show that there's a lot of them, therefore there must be at least one. I got in trouble for some of my exams at Williams, so I gave this as a exam question one year. Tell-Seward's theorem, how many of you have heard of this? So it's nice. Dirichlet's theorem requires A and B to be relatively prime. This theorem does not. Let A and M be any pair of positive integers, then there are infinitely many composites congruent to A mod M. Anybody give me a proof of this? So I give you any two numbers. They don't even have to be relatively prime. There are infinitely many composites congruent to A mod M. Any thoughts? Yeah.
So if A is not prime, you should use. Oh, I guess A is not prime. But you could use like M times A.
Okay, so oops, I forgot to change font size. So if A is greater than 1, look at, say, n times AM plus A. And that would work. Well, what if A equals 1? So I'll leave that as an exercise. Hopefully you won't be bored during the rest of this talk or the other talks later today, but you might have an English class later. So see if you can figure out what to do if A equals 1. Can you give me a constructive proof? Now, what was the last method we used a moment ago to prove something exists? Sorry? Show that there's infinitely many. So another way of looking at this is we basically dropped a nuclear bomb on the problem. This nice little problem, show that there's one prime congruent to A mod B. We proved a lot more. We know that the number of primes, if you know the prime number theorem, how many of you have seen the prime number theorem? So the prime number theorem says if pi of x is the number of primes less than or equal to x, pi of x is about x over log x. So if you think about how many integers are there congruent to A mod M, that's a positive percent of integers. The percent of numbers that are prime goes to 0. Therefore, almost every A mod M must be a composite number. So this is another nice way of proving that it's an overkill. This is not necessarily a great proof. I should not have to use something as powerful as the prime number theorem to prove that there are infinitely many composites congruent to A mod M. So a lot of times when we're doing proofs, we want to get a sense of how deep is the result. What do you really need to prove this? If you're looking at some advanced papers in number theory, you frequently have the professional mathematicians using the best known bounds. But we don't often need the best known bounds. What's the weakest thing you need to make something work? How many of you have seen the bridges of Königsberg? So the problem was you want to walk across the city and you want to cross each bridge once and only once. Is this possible? And this is one of the first graph theory problems. Anybody know if the answer is yes or no? I'm seeing a lot of no's. Can you give me a quick reason why it's a no?
Because one of the vertices are more than one vertice of degree 3. So it's not whether so you the thing.
You're close. Because I can stop and start at different vertices.
Every vertex has odd degree.
Every vertex has odd degrees. So even if I take one for the start and one for the end, for everything else, if I enter, I then have to leave. And so it would have to be an even number of edges. And so this is proof by parity. So since every vertex has a odd degree, I know there's no way to cross each bridge once and only once, no matter where I start, no matter where I end. So parity arguments are great. All right, so what I want to do now is turn to the main problem I want to consider, the Sperner or the triangle game. And so I will put my own money on the line. Worst case, it's a donation to Yale or Williams, both schools that I'm affiliated with. And I will play against you. If any of you do know Sperner's lemma, you are now mute. Does anybody know Sperner's lemma? So here's how the game works. Because I am a good number theorist, I start counting with 0. So I will label the vertices 0, 1, and 2. And then I'm going to subdivide my triangle into smaller triangles. And on the bottom, I can only use 0s and 1s. On the right side, I can only use 1s and 2s. And on the left side, I can only use 0s and 2s. In the interior vertices, I can use any number. You can use any number. And the goal for me is to have one of the smaller triangles labeled 0, 1, 2. If even one triangle is labeled 0, 1, 2, I win. Your job is to make sure that doesn't happen. And so you can all be a team. When I teach classes at Williams, I try to do this on a day when we have prospective students. And I tell them, if you win, you get free tuition to Williams. And I have to go to admissions and promise that, if they happen to beat me, I will put up at least 10%. I will give you $100 if you beat me. If we alternate moves. If you want to do 2 moves for every move I do, I will only provide $50 if you win. If you want to get 3 moves for every move I do, I will give you 25. And so on and so on. When I was doing this a few years ago with high school students, one of the high school students asked, and she's now actually, I think a math major at Williams, can we bank moves? I will allow you to bank moves. So I need somebody to be team captain.
Are you going first?
I'll let the team captain decide. You got, I will defer.
Are we trying to get triangle 0, 1, 2?
No, you are trying to prevent there being any 0, 1, 2 triangle.
And we can use numbers other than 0, 1, 2.
No.
Oh.
You have to use 0, 1, 2. Right? And I mean, whatever you put on the bottom has to be a 0 or 1. Whatever you put on the left side has to be a 0 or 2. And in the center can be either a 0, 1, or a 2. Okay. So do we have somebody who is willing to be team captain? Okay, who are you volunteering? Are you been involved? Okay, Benjamin, thank you. I mean, first you're a pirate, now you're a captain. It's a very naval day for you. Okay, so you get the choice. Do you want to go first or second? And you're allowed to bank moves.
Let's go second.
Stupid. You're a really bad captain. Yes, he is. Why was that a bad choice? You can always bank your first moves. So you should go first and bank them. You don't have to use them, right? So if you want me to go first, that's fine. Just say you go first and you get the moves to bank. That's what he meant. So what are we playing for? We're playing for $100, $50, $25, $12.50. Tuition at Williams. I can get up to okay, tuition at Williams. I have a blank check on me, tuition at Williams. So you are letting me go first.
Taking moves first.
I'm sorry?
Banking moves first.
Bank moves. And but you have to tell me, are we doing 1 to 1, 2 to 1, 3 to 1?
Well, it seems the financial incentive has become associated with this choice, so we may as well choose 3 to 1.
3 to 1. I'm not quite sure how this happened, but okay, so now we're playing for tuition to Williams, and you get 3 moves for every move I did. I'm gonna watch this video again because I do not think this is how the game is supposed to go. But all right, I'm gonna start off. Let's see, 2 is on the top. I'm gonna put a 2 here directly on. Is everybody able to see that? It just takes a few seconds for it to zoom from here to the laptop and then to get from the laptop to there. I could, yes. I'm playing for Williams tuition here. I'm not gonna make it easy on you. You squint, you move up. Fine. Well, actually, we're playing for Williams tuition. All right. We'll use a big purple 2. All right. So you have in the bank right now, you have 3 moves. So you have up to 6 moves right now. Right? Because this is your second turn. So where do you want to go? So we have a bunch of talks to get to later today, but we have time. You could, of course, bank again and not move at all. Do we want to pause and let people play with this for a minute on the boards? We're only playing this once. I'm not playing twice after you've seen the game play. We're doing this once, not twice. I'm going to just pause the video. So there is a conjecture that all labelings of the triangle will lead to a 0, 1, 2 somewhere. Now, is that a hard conjecture to prove for a graph like this? This is a computation that you could do. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think 11 things to do. So we're talking about 3 to the 11. Yeah, that's probably doable. And you can probably do a couple things with symmetries and whatnot. So you could probably do this by brute force and determine whether or not it's possible. Of course, I could give you a bigger and bigger and bigger triangle. Right, and so for that one, and so is there a way to build that up? So one of the things this whole colloquium is about is how do you prove things? So do you want to actually finish the game? Or do you think it's not worth it?
I want.
All right. You want to come up here and you've got 6 moves, go.
Oh boy, okay, I'll do it. If I can leave my prison.
All right.
It is a little bit of a prison.
All right, you've got 6 moves, and you don't have to use all 6, you can bang.
Okay. Think we discussed putting.
You're going there?
I mean, we're gonna lose, but.
2. So yeah, it's trying to have a huge block of 2s.
2.
So you've got 3 moves left.
2.
And you can bank or you can keep going.
2.
Okay, that's it. You've done 6 moves. Oh wait, no, you've done that.
I've done
twice.
5.
You've done that
Oh wait, I
twice.
did that twice.
You
You're
did
so
that
right.
twice.
Oh yeah, I want it here.
Okay.
Wait, I lied. I don't want it here. I want a bank.
Okay.
Now I'm done. No, does he win already?
If you didn't erase that one.
If you didn't erase that one, I was going to win.
Oh, okay, then it's good I erased it.
And so what I'm going to do is I'm going to toy with you and I'm going to put a 2 there. I'm going to do the move that would have given me the win. It's now your turn. You have 3 moves.
Okay, wait, no, I can recover
Well,
this.
you know you have to put a
A
0,
0 there.
and you have to put a 0 there.
Yeah.
And-
Ah.
It just gets pushed closer to the same one.
And now what do you want to put here? Do you want to put a 1 or a 2?
I would like to put a 1,
Okay.
but oh yeah, I get one more move. 1.
Well, you could run up there as well, but you have
I
to
guess.
put it anywhere. Actually, I'll let you move more than you should have.
I think
I'll
so.
let you move more than you should. All right, so at this point, we do have a 0, 1, 2. And we didn't label that. We'll label that 2 just for kicks and giggles. Okay, so I triumphed, but it wasn't clear that I was going to triumph, right?
Mhm.
And for a while it looked like you might have been able to prevent me. You had this forest of 2s coming down. You could try to do this on a small triangle and build up and see if it always exists on a small triangle, must it exist on a larger one? But things don't fit as nicely as you would hope for the induction like that. you can play this on smaller boards and try to build up intuition. We should never have played it on a triangle this big. What size triangle should we have played it on? Yeah, the triangle we have right over there, which coincidentally, is the next slide. And so we have 0, 1, and 2. Without loss of generality, what should I label the bottom right here? 0, right? And since we're labeling that 0, we can't label this piece over here 2. What do we have to label that? 1. So now over here, we can't label that a 2, or we would have a 0, 1, 2 triangle like that. And we can't label it a 1. Oh no, we're not allowed to do 1. We can't label it a 0, because then we'd have a 0, 1, 2 triangle there. So we've quickly proved that it's impossible to prevent me from getting a 0, 1, 2 triangle on this. But it's not clear, how do you take the impossibility of a small triangle and expand it upwards? So one of the big things I try to convince my students of is that they're often looking at the wrong problem. Is they have a problem that they're given, and it might be the problem you care about, but it shouldn't be the first problem you look at. So 2 of my friends at Yale left Yale for a year to help the amazing James Randi set up his institute to debunk psychics. And so with this being recorded right now, I will not say certain things, but I will talk to you over tea. It's very easy to put things in a certain way to get people to look at things in the direction you want them to. And so when I'm asking you what's an easier version of the game to play, does everyone agree that this is an easier version of the game to play? This is not the version of the game that you should play. Can anybody think of a better version of this triangle game that we should play? Where I have a triangle, I have the label 0, 1, 2. What could I do instead of studying a triangle game like this? An interval, right? This is a 2-dimensional game. Let's try to look at a 1-dimensional game. And so what's going to eventually come into play is the Brouwer fixed point theorem. All right, so just, for the experts in the audience, giving something a little bit away, if we have a nice continuous function from a nice set to another nice back to itself, it has to have a fixed point, a place where f of x equals x. I don't want to go into too much details about what this is going on here, but that will lead to Sperner's lemma that no matter how you divide it, there's always going to be at least one 0, 1, 2 triangle. And they don't have to be nice equilateral divisions. This was a definitely non-equilateral division. And you can see that we do have several 0, 1, 2 triangles. All right, but as was suggested, let's look at an easier game, build intuition, and maybe that can be extended. So I can't go from a smaller triangle to a bigger triangle, but I can go from an interval to a triangle. With our success in the triangle only a few minutes away, what will we do after that? After succeeding on the triangle, what will we do next? I'm sorry? I'm sorry? Yeah, 3 dimensions, the tetrahedron, right? And so let's look at Sperner's lemma on the line. So I label the left 0, I label the right 1, and everything in between is either a 0 or 1. And I claim there has to be at least one segment labeled 0, 1 or 1, 0. And the proof is very straightforward. If I want to try to stop it, what do I have to have all the labels as I march to the right from the 0? What do they all have to be? They all have to be 0. And as I march to the left from 1, what do they all have to be? They all have to be 1. And so you can see that eventually they're going to clash, and there has to be at least one 0, 1 segment. So that proves there will always be at least one 0, 1 segment. There's a better proof than this. And it's a proof that's going to give us more information. And so let's consider the possibilities. I could have a 0, 0 segment. I could have a 1, 0 segment. Do we all agree that by symmetry 1, 0 and 0, 1 are the same? And if I can understand 0, 0, I can understand 1, 1. It's the same kind of calculation. And I can put in a new dividing point. And I can look and see what happens to the number of 0, 1 segments. If I put in a 0, there's no change. And if I put in a 1, it changes by 2. All right, so if I put in a 1 for that middle point, I now have 2 0, 1 segments. Over here, if I put in a 0, there's no change. If I put in a 1, there's no change. And the calculation is the same for a 1-1 segment. So what we note is the number of 0-1 segments, the parity is unchanged when we put in another point and label it. So this is going back to a parity argument. And so just, writing things up a little bit more neatly and nicely, this is showing you all the different cases. How many 0-1 segments do we start with? 1. And so we know we have to end with what? An odd number, and an odd number is greater than 0. So this is another way to prove that something exists. You count it and show that the number of thy counting is odd. Therefore, it's at least 1. And so what I'm going to do, and I think at this point it's safe for me to take back my check. So only once was I ever doing a game where they slightly changed the rules and I did have a chance of losing. These games are always rigged. The question is just how easy is it to find the rigging? All right, so what do we know about any labeling of a triangle in this situation? What's the only thing we know? So what did we just prove a moment ago?
It always exists.
Always exists what? Well, no, we're going to prove that now. So we don't know that. We don't know that there exists a 0, 1, 2 triangle. What do we know exists?
Along like those edges, there's like 2 different numbers that need to be next to each other.
Good. So we know on the bottom there's at least there's an odd number of 0-1s. On the left is an odd number of 0-2s, and on the right there's an odd number of 1-2s. I'm going to just focus on the 0-1s. So we know there's on the bottom odd number of 0-1 segments on the bottom. Now let's count how many 0-1 segments there are. I'm going to count them by looking at triangles. So which triangles could have a 0-1 segment? What could the vertices be of a triangle that would give me a 0-1 segment? 0-1. Okay, so I could have T0-1-1, T0-0-1. What else?
Or you could have 0, 1, 2.
T0-1-2. So, and again, I'm going to consider 0-1-0 the same. Just doesn't matter where I start. How many 0-1 segments does this give? Does the first one give? Gives 2 0-1 segments. What about the second one? Gives 2. I can just go like this. Also gives 2 0-1 segments. And what about the last one? Gives 1. Okay, so let's count how many 0-1 segments there are. Every internal 0-1 segment, how many times is it counted? If I count triangles, so all the triangles that I have, if there's an internal 0-1 segment, it's in 2 triangles. So all the internal 0-1 segments are counted twice. All the external 0-1 segments are counted once. So if I look at the number of 0-1-1 triangles plus the number of 0-0-1 triangles plus the number of T0-1-2, what is that going to count? Well, let's put a little weight. Let's put a 2 times the 0-1-1, and let's put a 2 times the 0-0-1, and then we'll put a 1 times the number of 0-1-2. What does this count in? So does this count the number of 0-1 segments?
counts the number of adjacencies between 0, 1 segments and triangles?
So any segment on the outside is counted once and only once. Any segment on the inside, how many times is that counted? Twice. And if I look at this, how many 0, 1 segments does this triangle have? It has 2. How many segments does this one have? It has 2. How many does that one have? That has 1. So this is the hardest part of the proof, is to figure out what have we just counted.
It's like the triangles and the C1 just so the C1 that just belongs to the triangle.
So it's the number of
Yes.
pairs of,
Triangles and H.
okay.
So the H belongs to the triangle.
What do you think we've counted?
I don't know, I was thinking. Like the number of segments that make up all of the little triangles.
Well, do you agree that this has counted every 0, 1 segment? Every 0, 1 segment has been counted. Have any been counted more times? Which ones? So this is equal to the number of 0, 1 segments. And then which ones have been double counted? Plus the number of internal 0, 1 segments. Right? Another way of looking at this is equal to twice the number of internal 0, 1 segments plus what? External. And again, think back to the cube. If you look at it the right way, it becomes clear. What's the right way to look at it? I know that the number of 0, 1 segments on the bottom is odd. I somehow want to have that coming into my answer. I want to rework these formulas so that the number of 0, 1 segments on the bottom comes into play. I now have that. That's now showcased over here. And we know this is odd. What do we know about twice the number of internal segments? Even. So this whole number has to be odd. Therefore, what must be true about this? If we have the stuff in front of it is even. Right? What's the only thing that's left for this number to be? It has to be odd. So this is a nice way of showing that there has to be a 0, 1, 2 triangle. Is because I know that there's an odd number of 0, 1 on the bottom and everything in the interior is double counted, the number of 0, 1 segments in this counting is going to be odd. And since these ones are each generating 2 0, 1 segments each, and the 0, 1, 2 triangle is only generating 1, there must be an odd number of 0, 1, 2 triangles. Therefore, there has to be at least 1. And in fact, more than there has to be at least 1, there has to be an odd number. So we actually proved more than we were initially thinking about. Okay, so we've proved Sperner's lemma. Oops. And now what I want to do is I want to improve this game, because this game, I think you agree, sucks. Well, at least it sucks for you. I mean, for me, this is a great game. I'm really risking nothing. So this is now how you do math research. You can be glad that you proved something. And the fixed point theorem that's lurking behind this was actually used by Nash in his Nobel Prize arguments. How could you make this or the one-dimensional game more interesting? And there's lots of things you can do. I'm just curious as to what would you choose to do? Yeah.
Increase the dimension. The tetrahedron thing.
So you could increase the dimension. If you increase the dimension, I'm still going to win. It's gonna keep propagating up. It's a good thing to try, but I'm going to win. So you could, so try. Oh, sorry, I think we want to shift from that. Try squares and 4 colors. And so, maybe if you do something like that, now you have a chance. That's absolutely one way to do it, is use a different geometry. What else could you do? Anything you say is gonna work. Yeah,
Restrictions on the border,
I'm sorry,
no restrictions.
no restrictions on border. And you saw that at one point you were in trouble because you had no way to color something legally on the border, but if you could. In fact, maybe you just have all 2s coming down at some point. Yes, so wait. Say that again?
Maybe if you have different numbers, 0, 1, 2.
What do you mean by different numbers?
I mean, you prove that you have to be off number,
Right.
but what if I require an even number?
Well, if you require an even number, then I can never win. But you can modify yours. No, but you can modify yours. I have to have what to win? So we know I'm gonna have an odd number, and we know I have to, so what could you say? I have to have at least 3. Have at least 3 to win, right? And you could do the same thing on the lower board where you have an odd number of 0, 1 segments. You could basically say, okay, I know you're gonna have an odd number of 0, 1 segments. We're gonna subtract 1 from what you get. And you need to be able to beat me by that. And so the last time I gave the talk was, higher dimensions. That was the first thing said both here and then. Different shapes. What if you played this on a torus? Not just on a square, but what if you changed the geometry a bit? You could do it on a polygon with n sides. So this is generalizing the square. Labeling edges and faces. More labels. So there's lots of different things you can do to try to make the game more interesting and fun. So right now, as I said, I'm working with some students in the Polymath Junior program to try to make the game more interesting. And there's a lot of calculations you can do. One possibility is maybe you win if you beat the expected number. So one of my favorite theorems in probability is the expected value of a sum is the sum of the expected values. It's not true for the variance unless things are independent. It's not that hard to calculate the expected number of 0, 1, 2 triangles I would get if we were both completely drunk and just putting in labels willy-nilly at random. And so maybe you win if you can keep me below the amount I'm expected to have. So there's lots of things you can do. If we had more time, this is just showing the simulations work really well. I think this was 10 million simulations. The predicted number was 22.222222. The observed was 22.22155. So pretty good alignment. Look at special cases. Try to play the game on the line. This is a simple enough situation that you might be able to build up some good intuition of what's going on. And the advice I'm going to leave you with is try to do simple problems first, build up your intuition there, and then push it forward. Try to come up with good natural next questions to ask you. Once you've solved the problem, what's the next thing you can do? What are the fundamental obstructions that prevent you from going further? What was the key idea that allowed you to solve this? So I will just end with thanking everybody for the invitation, both myself and my students to come here. It's been a lot of fun coming back. So thank you.